Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 4 for January 2025. Let's begin with the first question. In question 1, which reducing agent is used to convert carboxylic acids to alcohol? This should be lithium tetrahydroaluminate 3 in dry ether, so the answer is D. Then in question 2, polyester is made from pentane, 1,5-diol and pentane-dioic acid, which is a repeat unit of this polyester. So if these are what we use to make, this should be crossed out or it should have gone out. So this is going to be wrong. The dicarboxylic acid should have 5 carbons in total, but if we have 5, 6, 7, this is wrong. And over here we see these are 5 and those are 5, which should not be right. So this is also wrong. This is correct. We have 3 for 5 for the pentane-dioic acid. And here we have the 5. Also, the oxygen has gone away from this carboxylic acid and it's only left on the alcohol side. So the answer is C. In question 3, when ammonia dissolves in water, an equilibrium results. Equation for this reaction is shown. Which of the base species acts as a bursted lauric acid in this equilibrium? So this should be an acid that donates a proton. In this case, we see water is donating a proton to become OH-, and this one here is receiving it to become that. So the answer should be D. In question 4, a strong monoprotic acid of concentration that has a pH of 2. What is the decrease in pH if the concentration is increased by that? If it's strong and monoprotic, then it gives away all the hydrogen ions. So this is also going to be the concentration of the hydrogen ions. So at 0.011 concentration, the pH is going to be negative log of that concentration, which gives us 1.96. So the decrease or change in pH is going to be 2 minus 1.96, which is 0.04, and the answer is B. In question 5, one of the stages in the manufacture of sulfuric acid involves the oxidation of sulfur dioxide to sulfur trioxide. The equation for this reaction can be written in either of the two ways shown. So equation 1, we have the sulfur dioxide reacting with oxygen to give us that, and this is basically half of equation 1. This is the value of Kp at 25 degrees Celsius using equation 1 is 4.0 times 10 power 24 per atmospheres. What is the numerical value for Kp at 25 using equation 2? We see equation 2 is half of equation 1, meaning to find the Kp of this, we're going to get the square root of the Kp of the first equation. So Kp2 should equal to the square root of Kp1, which is equal to the square root of the value given. And so the answer is 2.0 times 10 power 12, which is A. In part B, the relationship between Kp and Kc is shown. We see this relationship. They say where T is the temperature in Kelvin, R is the gas constant, and change in N equals 2 moles of product minus moles of reactant. What is the value for Kc at 25 degrees Celsius for the equilibrium using equation 1? So here, for equation 1, remember we've got the Kp. It's 4.0 times 10 power 24, so substitute that here. We have the R value 0.082, and then the temperature, it's 298 because it's 25 degrees. Change in number of moles for this is going to be, we see here there are 3, and these are going to be 2, so 2 minus 3, it's going to be minus 1. So power minus 1, and the answer I got 9.77 times 10 power 25, so D is the answer. Question 6, which equation represents the standard enthalpy change of atomization of iodine? Here they say standard, and iodine at standard conditions is going to be a solid. Enthalpy of atomization, this is when 1 mole of gaseous atoms is formed. So we will look for an equation where iodine comes from solid to 1 mole of gas. And we see this is what qualifies. 1 mole of gaseous iodine is formed from solid iodine. The answer is going to be A. And in question 7, which equation represents the second electron affinity of oxygen? Electron affinity is about gaining electrons. So if it's gaining the second, it's already negatively charged and gaseous. So gaining to become O2 minus gaseous, the answer is A. In question 8, which compound has the greatest covalent character? This should be the metal ion, which is really small, highly charged, attached to a very big non-metal ion. So among the non-metal ions, iodine is going to be the biggest, and among the metal ions, magnesium is going to be the smallest. since all the metal ions have the same charge, then magnesium iodide is going to be the answer. In question 9, which pair of values will always give a thermodynamically feasible reaction? They said always. Remember, the S total equals the S system minus delta H over T. So to ensure it's always positive, then this is going to be negative. Delta H should be negative and this should be positive. So the answer is going to be C. In question 10, this question is about the effect of changes on a system at equilibrium. The equation for the reaction between hydrogen and iodine is shown, which is that what is the effect, if any, of an increase in the pressure of the appearance of the equilibrium mixture? Now here, increasing pressure shifts the equilibrium position to the side that has fewer gaseous molecules, but the problem here, they both have the same number of gaseous molecules, so there will be no overall change. However, increasing pressure compresses or puts both closer to each other, and so the color of iodine is going to be seen, so the mixture becomes more purple. Then in part B, the equation for the manufacture of ammonia by the Haber process is shown, which is that, and Kp value is given, which changes, if any, will result in increase in the value of Kp. Remember, Kp is only affected by temperature, so in this case, since the forward reaction is exothermic, you will decrease the temperature, so the answer is going to be B. And in part C, the equation for the equilibrium between nitrogen dioxide and dinitrogen tetroxide is shown. A change in the conditions results in Kp increasing from that to that. What can be deduced about the change in position of equilibrium? If an increase in Kp, like here from here to here, if it increases, it means we have more product that is being formed. The equilibrium position has shifted towards the product side, so the answer should be A. In question 11, what is a pH over 0.1 mole per decimeter cube solution of sodium hydroxide? Now, when sodium hydroxide ionizes, it releases 100% of all the OH, meaning the sodium hydroxide concentration equals to the hydroxide concentration. And so in this case, concentration of hydroxide is that, and pH will equal to the pKw, which is given here, minus pOH. And pOH is going to be negative log of that. So 14.53 minus negative log of 0.1 gives us 14.53 minus 1. And the answer is 13.53, which is B. In question 12, the pH of a dilute solution of a weak carboxylic acid can be calculated from its Ka value, which is not a relevant assumption in the calculation. We usually assume that the acid dissociation, or in this case, the weak acid dissociation, is really minimum, whereby the equilibrium concentration of this weak acid and the initial concentration are exactly the same, and also the dissociation of water is negligible. So when they say the ionization of water is insignificant, this is correct. It's relevant. The initial and equilibrium concentrations of the acid are the same, that is relevant. The concentration of the protons and carboxylate ions are the same, yeah, we do that. And the dissociation of the carboxylic acid is almost complete, that is wrong. It's not relevant. It's not a relevant assumption. In question 13, this is a question about buffers. The Henderson-Hechobach's equation can be used to determine the pH of a buffer solution, and the equation is this. What is the pH of a buffer solution containing 0.1 mole per decimeter cubed ethanoic acid and 0.2 mole per decimeter cubed sodium ethanoate? So here we just substitute pH will equal to pKa. You would say negative log of 1.7 times 10 power negative 5 plus concentration of the salt, which is 0.2, divided by the concentration of the acid, which is 0.1. So this is the same as, this gives 4.77 plus log of 2. And using the calculator, I got 5.07, and C is the answer. In part B, what is the best reason for the use of buffers in foods? This is to prevent the deterioration by fungal activity. It could be fungus or microorganisms, not to improve taste, not to help with digestion of food, and not to enhance color or appearance. The answer is C. In part C, said hydrogen carbonate ion buffer system in the blood involves the equilibrium shown. How is the pH of the blood affected by increase in exercise? During exercise, carbon dioxide is released, so more of it shifts the equilibrium position to the other side. In question 14, which has the greatest molar entropy? Molar entropy increases from solids to liquids to gas. So since we have gases, I'm going to exclude the liquids, And among these two, this one has more numbers of atoms, more number of electrons, and therefore more disorder, so the entropy will be the greatest. In question 15, a graph of the concentration of Q during decomposition is shown. So down they say, what is the half-life for this decomposition? So I began from 9, which is at 0, and I went at 4.5, which is about 132. So the half-life is going to be 132 minutes, and so B is the answer. In question 16, this question is about pentan-2-on. Explain why pentan-2-on has a lower boiling temperature than pentan-2-ol. This is a ketone and this is an alcohol. This alcohol can form intermolecular hydrogen bonds with other pentan-2-ol molecules, but pentan-2-on cannot form intermolecular hydrogen bonds. So I said pentan-2-ol contains an OH group which allows to form hydrogen bonds between molecules. Pentan-2-on only has London forces and permanent dipole-dipole interactions, which are weaker than the hydrogen bonds. Therefore, more energy is required to break the intermolecular forces in pentan-2-ol, so it has a higher boiling point. In part B, give a chemical test which distinguishes between pentan-2-on and pentan-3-on. If you go back to pentan-2-on, you can see it has a triminomethyl group, so meaning we can use iodine in the presence of sodium hydroxide. So a positive test is going to be seen with this because of the CH3CO group, so it will form yellow precipitates of triiodomethane. In this one here, we'll have no observable change. In C, they say, give a different chemical test which distinguishes between pentan-2-on and pentanal. This is an aldehyde and this is a ketone. So here we can use either Tollin's reagent or Fehling solution. So pentanal, which is the aldehyde, will form a silver mirror with Tollin's reagent. And if you use Fehling's, it will form a brick red precipitate. Pentan-2-on will have no visible change with either of the reagents. In part D, pentan-2-on, pentan-3-on, and pentanal react in a similar way with one test reagent to form solid products. Identify the reagent and describe how these solid products may be used to distinguish the original compounds. This is 2,4-dinitrophenylhydrazine, which is a test for carbonyls since all three compounds are carbonyl compounds. After you get the precipitates, you can filter them and then recrystallize them. Wash them with minimum amount of cold solvent in order to take out any impurities, and then get the melting temperatures and compare with data booklet values. So in part E, pentan-2-on and pentan-3-on both react with hydrogen cyanide in the presence of KCN. With pentan-2-on, a racemic mixture is formed, but with pentan-3-on, there is only one product. Explain the difference by referring both to the reaction mechanism and the structure of the two molecules. So this is going to be nucleophilic addition reaction. So I say the reaction mechanism is nucleophilic addition to the carbonyl carbon in pentan-2-on. The carbonyl group is planar and bonded to two different groups. Attacking by CN can occur from either side, forming two enantiomers leading to a racemic mixture. If you look at pentan-3-on, we can see this is a CH2CH3 and a CH2CH3. So even if the CN comes in here and we form OH up here, we have two groups that are similar, so there is no chirocarbon. So I went on to say the carbonyl compound is bonded to two identical ethyl groups, making it symmetrical. Attack from either side gives the same product without a chirocarbon. In question 17, esters are difficult to distinguish from each other using chemical tests, so NMR spectroscopy is often used. There are 4 ester isomers with the molecular formula carbon-4 hydrogen 8 O2. Their display formulae are shown. So they say explain which of the 4 esters can be distinguished from the other 3 by the number of peaks in the carbon-13 NMR. This one has 1, 2, 3, 4, and this one has 1, 2, 3, 4. This is 1, 2, 3, 4, and here we have these two are identical. So 1, 2, 3. We can distinguish ester S because it will show only 3 peaks while the others show 4 peaks. So I said ester S can be distinguished. It contains only 3 peaks, and PQR contain 4 peaks. Then part B says there are 9 ester isomers with a molecular formula that the displayed formulae of 2 of these esters are shown. They say ester W and X both have 1 peak, with a relative area of 3 in their low-resolution proton NMR. Explain how these peaks can be used to distinguish these two esters. So we have a CH3 here and then a CH3 here. This is HCO, while this is HCCO. They can be distinguished using the chemical shifts. So I said both esters have a CH3 group giving a singlet with area 3, but their chemical shifts differ. In W, the CH3 is bonded to oxygen as HCO, so its chemical shift is 2.8 to 4.2 ppm. In X, CH3 is part of an ester group, HCC double bond O. The chemical shift range is going to be about 1.6 to 2.8 ppm. Then they say the displayed formulae of two different esters are shown in the boxes. Label the displayed formulae of two esters Y and Z to show the proton environments and the splitting patterns of the peaks in the high-resolution proton NMR. Clearly indicate any equivalent proton environments. So I'll begin with this one. This is A. I'm going to call this B, this C, this D, and that E. Now, environment A is a triplet. Why? The nearby carbon has 2 hydrogens, so 2 plus 1 gives us 3. Environment B is a quintet. Why? We have 3 here and we have 1 here, so 4 plus 1 gives us 5. And environment C, the C here is connected to this, which has 2, and the other side we have 3, so those are going to be 5 plus 2, we get 6, so sextet. Environment D connected to this carbon that has 1, and so it's going to be 1 plus 1, which is 2, doublet. And this one here, the carbon is not attached to anything with a hydrogen, so this is a singlet. And in ester Z, these are identical. These CH3 and CH3 are identical, so I call them environment A. This is B, that is C, and that is D. Now for splitting, this here is going to be a doublet because the neighboring carbon has only 1 hydrogen and 1 plus 1 is 2. Then when we go to environment B, the neighboring carbon has 1, 2, 3, 4, 5, 6, and this side 7, 8. 8 plus 1, we get 9, so nonette, or you could say split into 9. Then we go to environment C. This has 2 hydrogens, but the neighboring carbons has 1. 1 plus 1 is 2, doublet. And this one here is a singlet because there is no hydrogen on the next atom, so it's singlet. Then they said draw the displayed formula of the carbon 5 hydrogen 10 O2 ester, which has only 2 peaks in the low resolution NMR structure. If it has 2 peaks, then these are going to be identical, meaning these protons are all identical to 9, and only one is going to be the other side. So this should be the structure. This question is about reaction kinetics. Halogenoalkanes are hydrolyzed by aqueous alkali to form alcohols, like we see here. The right equation for these reactions with 2 halogenoalkanes are shown. So we see 1 bromobutane and then 2 bromo 2-methylpropane. Explain how these rate equations can be used to deduce the different reaction mechanisms of the reaction of hydroxide ions with these halogenoalkanes. So we can say this is basically SN2 and this is SN1 because the OH has not appeared in the rate equation, meaning it's not part of the slow state. Here we can see the OH appears, so it's part of the slow state, SN2, SN1. So here I said 1 bromobutane has a rate that depends on OH minus, as you can see there, indicating that both the halogenoalkane and hydroxide ion are involved in the rate determining step. This suggests an SN2 mechanism, which is a one-step reaction where OH directly attacks the carbon bonded to the halogen, displacing the halide ion in a single step as a transition state forms. 2-bromo 2-methylpropane has a rate that only depends on the halogenoalkane, not OH minus. This suggests an SN1 mechanism, which involves a 2-step process. In step 1, which is slow, formation of the carbocation intermediate after the halide leaves, and step 2, which is fast attack of the OH on the carbocation. Tertiary halogenoalkanes like 2-bromo 2-methylpropane form stable carbocations, making SN1 favorable. Primary halogenoalkanes like 1-bromobutane do not form stable carbocations, so they undergo SN2 instead. In part B, an initial rate method may be used to investigate the kinetics of the reaction between hydrogen peroxide and iodide ions in acid solution. The equation for this reaction is shown. We have that. The reaction mixture contains a small amount of thiosulfate ions, which reduce the iodine back to iodide ions. This equation for this reaction is what we see here. As soon as the thiosulfate is used up, the iodine that is further produced reacts with the starch present and results in a color change. The time taken for this color change is noted, and the reciprocal of this time is used as a measure of the rate. The results from a series of experiments where the volume of the hydrogen peroxide was changed are given in the table. So this is the table of the results, and they say give the color change after all the thiosulfate is used up. Remember, they said the iodine that is produced is going to react with the starch, meaning it's going to be colorless to blue-black. Then plot the graph of reaction rate against volume of hydrogen peroxide. So I use the results from the previous table. On the vertical axis, we have reaction rate times 10 power negative 2. This is per second. And on the horizontal axis, we have volume of hydrogen peroxide in centimeters cubed. And I had 1, 2, 3, 4, and these were 5 points, and a straight line through the origin. I went through the other 4 points except that. They say state and justify the reaction order with respect to hydrogen peroxide by using the graph. This is first order because it's a straight line going through the origin. Then in part C, the continuous monitoring method was used to investigate the kinetics of the reaction between magnesium and sulfuric acid at different temperatures. The equation for the reaction is shown. So here we see magnesium as solid reacting with sulfuric acid and giving us the product. And the graph shows the results at 80 degrees Celsius. So ignore the parts in blue, those I wrote them based on other questions. So the first part says calculate the reaction rate at 15 seconds using the tangent shown. Give your answer to two significant figures, include units if any. So for this, I use this point here and that point. This is 218 and that is 2458. So the gradient was 58 minus 18 divided by 24 minus 2, and I got 1.8 centimeters cubed per second as my answer. Then next, the temperature of the reaction was changed to 75, meaning it's a decrease. Draw a line on the graph to show the possible results if this was the only change. Just find any similarities and differences in the lines. So at a lower temperature, the rate is going to be slower than this initial rate. However, the maximum volume of hydrogen gained is going to be the same, so I drew it a little bit less steep, and then the volume maximizes at the same point. So I said at lower temperature, particles have less kinetic energy, fewer successful collisions per unit time, rate is lower, but total amount of hydrogen gas is unchanged. In question 19, many effervescent products such as vitamin tablets are solid, which contain citric acid, sodium hydrogen carbonate. Only when these tablets are added to water is fizzing observed. The equation for the reaction is shown, which is that. Give two reasons why this reaction is thermodynamically feasible when considering the entropy of the system. So here we can see it leads to an increase in the number of gaseous molecules, 3 molecules of gas. So these gases have a high entropy. I said increase in the number of moles of gas. The reaction produces 3 moles of carbon dioxide gas from solid and aqueous reactants. Gases have a high entropy, so the production of gas increases the entropy of the system. Also, change in physical state. The reactants include solid, but the products include gases and aqueous ions. This increases the disorder, contributing to a positive entropy change in the system. In part B, they say describe in terms of particles involved why the reaction does not occur until the tablets are dissolved in water. This is because the ions within the solid are going to be in fixed position. We need them to be freed by water for the reaction to increase. I said in solid state, the ions and molecules are fixed in a lattice and cannot move or collide with each other. When dissolved in water, the citric acid and sodium hydrogen carbonate dissociate into ions which are free to move, increasing the chances of successful collisions and allowing the reaction to proceed. Then in part C, for the reaction at 25 degrees Celsius, the standard entropy change of surroundings is that. Calculate the enthalpy change of the reaction, include a sign and units in your answer. The surrounding equals negative delta H over T. So if we have this, we can say delta H equals negative DS surroundings times T. And that is going to be negative of negative 234.9 times 298, because this is standard, so 25 degrees or 298 Kelvin. And I got that in joule per mole, which is kilojoules per mole. This is the enthalpy change. Then part D, the enthalpy change of solution of sodium hydrogen carbonate is that. Sketch the enthalpy level diagram to show the relationship between enthalpy change of solution, lattice energy, and enthalpies of hydration for the dissolving of sodium hydrogen carbonate in water. Now remember that enthalpy of hydration should be when gaseous ions are converted into aqueous ions. So we see there is going to be an exothermic reaction. And then lattice energies when these are converted into solids. So we see a sodium hydrogen carbonate solid formed. And then solution is going to be when this solid dissolves, since this is an endothermic reaction. And this is based on that value here. Then in question 20, they say oxalic acid has the IUPAC name ethane dioic acid and the molar mass of 90 gram per mole. The name oxalic acid originated from the fact that it was first isolated from plants of the genus Oxalis. The formation of oxalic acid in plants involves the hydrolysis of 2-oxo-butanedioic acid. Plants can also form oxalic acid from glycolic acid, which is this one. Oxalic acid can be manufactured by oxidizing sucrose using nitric acid in the presence of a vanadium 5 oxide catalyst. Over 100,000 tons of oxalic acid are produced each year. Much of the oxalic acid produced is used for cleaning or bleaching because it converts insoluble iron compounds into soluble iron salts. Calculate the atomic economy by mass for the formation of oxalic acid from the hydrolysis of 2-oxo-butanedioic acid. Then the molar mass of oxalic acid, we already know, actually I didn't need to calculate, it's 90. So atomic economy is going to be the desired product divided by the total products times 100, giving us 60%. Then part B says give the laboratory reagent and conditions required to convert glycolic acid, which is that, to oxalic acid. Do not consider nitric acid. Oxalic acid has 2 carboxylic acids, so to convert this to carboxylic acid, we will oxidize using potassium dichromate, or use a potassium dichromate 6 with sulfuric acid and heat under reflux. In part C, sucrose is oxidized by concentrated nitric acid to form oxalic acid. Complete the equation for the reaction of 1 mole of sucrose with nitric acid. So here, because this contains all the carbons, reactant side has 12, so 6 times 2, we create 12, so 6 is balanced here. And then we go to the nitrogens. The nitrogens here are 36N, so they should be 36. And then the remainder part, we can focus on the remaining hydrogens if you cancel out here, or you could use actually oxygens to balance this, and I saw it was 23. Then give one observation that will be seen during this reaction. Because nitrogen dioxide is formed, of course we're going to see some brown fumes. In part D, a solution of sodium hydroxide was titrated against 25 centimeters cubed of oxalic acid solution. Both solutions were of equal concentrations. A student sketched a curve to show the changing pH during the titration. This is going to be diprotic as well. So they say select one indicator for each equivalence point. From this titration graph, include the color at the end point of the indicator. Use the data booklet. So for the first equivalence point, because of the ranges, I can go with methyl orange. And then the second, because it's the upper part here, phenolphthalein indicator is going to work. When we use methyl orange, the endpoint color is going to be orange, and phenolphthalein, the endpoint color is going to be pale pink. Then they say suggested difficulty that would occur if the indicators were present in the same mixture. The two colors are going to interfere with each other, making it difficult to correctly pinpoint the endpoint. Determine by using the graph the 2 Ka values for oxalic acid. You must show you're working on the graph. So I'm going to go with the first one. We see the first equivalence point is at about 25. Half equivalence is going to be about 12.5. So the pH at half equivalence equals to pKa. Here I have about 1.3. Now for the second, we will get the volume from 25 to 50 because it occurs at 50. And that means the second half is going to be at this point, giving us a pH of about 5.5. So if we have pH 5.5 and 1.3, we know pH is equal to pKa and pH is negative log Ka. So Ka should be 10 power negative pH, meaning for the first one, it's going to be 10 power negative 1.3, giving us that. And for the second one, it's going to be 10 power negative 5.5, giving us that. So these are the two Ka values. In part E, spinach is one plant source of oxalic acid. Approximately 700 milligrams of oxalic acid can be extracted from 100 grams of spinach. High performance liquid chromatography, HPLC, is used for analysis in the extraction process. The HPLC equipment is connected to a detector which records peaks when substances pass through the HPLC column. Suggest how a pure sample of oxalic acid would be used to identify the oxalic acid peak in the chromatogram of spinach extract. So here you will use a pure sample of oxalic acid, run it through an HPLC machine to determine the retention time, and then you compare the peaks from the spinach extract chromatogram to identify the oxalic acid peak. The next they say a 0.558 mole per decimeter cube solution of oxalic acid is used for cleaning. Calculate the mass of spinach required to make 500 centimeters cubed of oxalic acid cleaning solution. So the mass concentration of oxalic acid, I'm talking about concentration in gram per mole, will equal to molar concentration times molar mass, which is this molar concentration times 90. We were given the molar mass, giving us that. Then the required volume of oxalic acid is 500 centimeters cubed, which is 0.5 decimeters cubed. So the mass of oxalic acid is going to be mass concentration times the volume, which is that times that, giving us 25.11 grams. We know that 700 milligrams, which is the same as 700 times 10 power negative 3 grams of oxalic acid, are given by 100 grams of spinach. So this is going to be given by 100 divided by 700 times 10 power negative 3 times 25.11, giving us 3587 grams if you round off. Lastly, write the equation for the reaction of oxalic acid with excess phosphorus pentachloride. If it's excess, it means all the OH groups are going to be replaced by Cl. So this is going to be 2 PCl5. One Cl comes in here and the other Cl will come in here. So we will get COCl plus 2POCl3 plus 2HCl. So this brings us to the end of question 20 as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.